So guys, soon after we have seen the purification of the colloids, in today's video we are going to deal with the properties of your colloids. So our heading will be what? The properties of colloids. Properties of colloids. Remember, basically we are going to study two important properties of your colloid. First is called as that of your optical property. Optical property. Of course, when you are hearing the word as an optical, you'll be getting a clue that we are going to understand that how does the colloidal particles are going to affect that of your light. And the second most important thing is the kinetic property, that is the energy associated with respect to that of your colloidal particles and what is the reason for their zigzag random motion. So now let us deal one by one. So first and the foremost thing, I would like to deal with a property called as that of your optical property. Basically, this optical property is being studied under the heading called as that of your Tyndall effect. What it is? Tyndall effect. So before going to this Tyndall effect, let me ask you a question. Yeah. Assume that you are sitting in a theater. Of course, everybody sits in a theater and you have also experienced it. Try to recall the incident. Yeah. Overall theater is dark, completely dark. Yeah. Only the projector light is being projected on the screen. I am once again asking you the question. Assume you're sitting in a dark theater, no light, okay, dark theater. Projector is on and the projected light is projected on the screen. The first question what I'm going to ask is, can you see that path of the projector light? Again, I'm repeating, can you see the path of the projector light? I'm waiting for your answer. Yes, we can see the path of the projector light. Very good, you have a good keen observation. Not only you're seeing the movie, even you're seeing the signs. Very good of that. Those who have not seen it, once again, as soon as this coronavirus breaks out, you can just go to the theater and observe it. Okay. And the second most important thing is, what is the shape of the path of that projected light? I am repeating, what is the shape of the path of that projected light? Yes, it is like that of your cone, alva. How it is? It is like that of your cone. That is, like this it would be, if you have seen. Now, if this is your projector, means it has been a divergent beam. True? Yes. So this is the effect called as that of your Tyndall effect. Now let us see something interesting, alva. Even we have seen the colloidal particles optical property in our day-to-day life, but we were not knowing the effect what it is causing it. In today's class, we are going to see certain things which we have missed in our day-to-day life. So first important property is the optical property, which is called as what? Tyndall effect. So let us understand, what do you mean by this Tyndall effect? Remember, generally, okay, in order to remember, I'm just saying for a generally, what do you mean by Tyndall effect? It is having its actual definition, which will be discussed later in this video itself. Remember, Tyndall effect means it is the scattering of light. What it is? Tyndall effect is the scattering of light. Scattering of light by colloidal particles. What it is? Scattering of light by the colloidal particles. So this is called as what? As that of your Tyndall effect. So where is this colloidal particles are existing? In a colloidal solution, alva. So what do you mean by this Tyndall effect? Main thing is, it is the scattering of light. It is the scattering of light. Scattering and the artha, ಒಂದು ಲೈಟ್ ಬಂದು ಬೀಳ್ತಾ ಉಂಟು ಒಂದು ಪಾರ್ಟಿಕಲ್ ಮೇಲೆ ಅಂದ್ರೆ ಎಲ್ಲಾ ದಿಕ್ಕಲ್ಲೂ ಅದೇನ್ ಮಾಡುತ್ತೆ, ತನ್ನ ಲೈಟ್ ನ ಡಿಸ್ಪರ್ಸ್ ಮಾಡುತ್ತೆ. ಸೊ ದಟ್ ಈಸ್ ದಿ ವರ್ಡ್ what we use instead of using the disperse, we use it as scattering. So ಏನಾಗುತ್ತೆ, Tyndall effect means what? It is actually the scattering of light by what? Colloidal particles in a colloidal solution. Is that much simple? Of course not. When the question arises, can we see the Tyndall effect normally? Then what we did actually, initially how it was observed, we had to go with a demonstration, experimental demonstration. What we did is, basically we took a beaker, okay, which was having what? Your colloidal particles plus that of your colloidal solution. Or you can just say as it was having what? A colloidal solution was present. Colloidal solution artha enu, colloidal particles ಮತ್ತೆ disperse phase ಮತ್ತೆ disperse medium ಎರಡು ಇತ್ತು. Okay. Then what we did is, we took a light source. So our light source na ಏನ್ ಮಾಡ್ತೀವಿ ಅಂದ್ರೆ, we are projecting it on this beaker. Remember, this beaker is not just a solution, instead it is a colloidal solution which is having your colloidal particles. So what did we observe over here is, basically whatever the light which projected from this source, it was scattered. What it was happening? It was scattered by that of your colloidal particles, and a bright cone was observed. So whatever we are seeing over here, this is actually appears as that of your bright cone, this part. So this part what will be seeing in the solution, this part, ee olgade part ಏನು ಇರುತ್ತಲ್ವಾ, so ಈ ಒಂದು part solution ಒಳಗೆ ನಮಗೆ ಏನು ಕಾಣಿಸ್ತಾ ಉಂಟು, this will be actually called as your Tyndall cone. ಏನು ಹೇಳ್ತೀವಿ ಇದನ್ನ? Tyndall cone. Can we observe it normally? Of course not. In order to observe it, we have to look after through a microscope at a 90 degree. ಏನ್ ಹೇಳ್ತೀವಿ, ಈ ಒಂದು ಟಿಂಡಾಲ್ ಕೋನ್ ನಾವು ನೋಡ್ಬೇಕು ಅಂದ್ರೆ ಮೈಕ್ರೋಸ್ಕೋಪ್ ಮೂಲಕ ನೋಡ್ಬೇಕು. ಯಾವ ತರ ಇರಬೇಕು ಆ ಮೈಕ್ರೋಸ್ಕೋಪ್ ಅಂದ್ರೆ, ಇಟ್ ಶುಡ್ ಬಿ ವಾಟ್? ಅಟ್ ಅ ರೈಟ್ ಆಂಗಲ್ ಅಲ್ವಾ, ಅಟ್ 90 ಡಿಗ್ರಿ ಅಲ್ಲಿ ನಿಮ್ಮ ಮೈಕ್ರೋಸ್ಕೋಪ್ ನ ನೀವು ಅಡ್ಜಸ್ಟ್ ಮಾಡ್ಕೋಬೇಕು. ಸೊ ದಟ್ ಪಾರ್ಟ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ ವಾಟ್? ಯೋರ್ Tyndall effect. So ಈಗ ನಾವು ಡಿಫೈನ್ ಮಾಡೋಣವಾ? So when light is passed through the colloidal solution, and when it is observed at a right angle, using a microscope, yeah, the path of the light is visible. What it is saying? The path of the light is visible in the colloidal solution as a bright cone. Ee one part ಕಾಣಿಸ್ತಾ, this will be actually very bright. Why this is observed? Only because of that of your scattering of the light by the colloidal particles in all the direction. So this phenomenon is called as what? Your Tyndall effect. So whenever you have been asked to say what do you mean by Tyndall effect, you have to answer in this way. What is that? So when a light is passed through the colloidal solution and it is observed at a right angle using a microscope, the path of the light is observed as that of a bright cone. And why we are observing it? Because of the scattering of the colloidal particles in all the direction. So this phenomenon is called as what? Your Tyndall effect. Okay. So what is this bright cone is called as? It is called as what? Tyndall cone. Now we are able to understand. Now the question arises. Now let us go back to the example. What did I ask you initially? What was that? Can you observe the path of the projector light? Of course the answer was yes, I can observe. What will be the shape of that path? It will be like your cone alwa, a sharp cone you could just see. ಈಗ ಕ್ವಶನ್ ಅರೈಸ್ ಆಗುತ್ತೆ, ಓಕೆ ಸರ್, ಇನ್ ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಅಲ್ಲಿ ನಮಗೆ ಕೊಲಾಯ್ಡಲ್ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಇತ್ತು, ಲೈಟ್ ನ ಸ್ಕ್ಯಾಟರ್ ಮಾಡ್ತು. ಹಾಗಾದ್ರೆ ನಮ್ಮ ಥಿಯೇಟರ್ ಅಲ್ಲಿ ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಬರುತ್ತೆ? ಸ್ಕ್ರಾಚ್ ಯುವರ್ ಹೆಡ್ ನಾವು. ಥಿಯೇಟರ್ ಅಲ್ಲಿ ಯಾವ ಪಾರ್ಟಿಕಲ್ಸ್ ಈಗ ಕೊಲಾಯ್ಡ್ ಹಂಗೆ ಆಕ್ಟ್ ಮಾಡುತ್ತೆ? ಎಸ್, which is the dispersed phase over there and which is your dispersion medium over there? Very good. So as soon as you are entering to the theater, what it would be? You will be having a continuous medium of air. But in that air, you will be also having your dust. That is your small particles of your solid. So air will be acting as what over there? Dispersion medium. Whereas your dust will be acting as what? Your dispersed phase. Alva. When you will be observing your bright cone, when you are raising your head above and making it at a 90 degree or a right angle, we can observe the path of the projector light as that of your cone. Is that true? So how can we observe it? Because whatever the dust particles which is present in the air, it is acting as a colloidal particle. And this dust, what it is doing? It is dispersing the light, or it is scattering the light in all the direction. And that is the reason we are able to see the path of the projector light in terms of a cone, which itself is called as what? Tyndall cone. And the phenomenon is called as what? Tyndall effect. You able to understand? Not only in that case, even though if when you are doing the Dasra exhibition, when you are going, the final day will be a laser beam show. Yes, the laser beam show also, what you can see, how can you able to see those laser beams in that night area? It is mainly because once again the Tyndall effect. Whatever the dust particles are present over there, what it is doing, it is scattering the light in all the direction. And that is the reason whenever you are seeing the path, you just observe it. Whenever you see the path of the light, you just on the light in a dark room, you can just see that path of the light will be like a cone, bright cone. Why it is bright? Only because of the whatever in that room or in that dark area, the dust particles are present that will try to scatter the light in all the direction. And that is the reason it appears as a bright cone. Remember, mark my words, appears as a bright cone called as a Tyndall cone. And whatever the phenomenon we are observing over there, it is called as what? Tyndall effect. So now onwards, whenever you go for an Dasra exhibition, for a laser beam show, or to the top of a theater, whenever you see those lights, it's to strike your mind, okay, this is the phenomenon of a science, which is called as what? Tyndall effect. What is Tyndall effect? Whenever a light is passed, yes, whenever a light is passed to a colloidal solution, and when it is observed, mark my words, and when it is observed at a right angles using a microscope, the path of the light is visible in the colloidal solution as a bright cone. What is that bright cone? Is called as Tyndall cone. Why it is observed? Due to the scattering of the light by the colloidal particles in all direction. So that phenomenon will be called as what? Your Tyndall effect. Okay. Similarly, in a foggy day, okay, of course you have not experienced it, but whenever you go for Delhi or somewhere there, you'll be able to see that in a foggy day or in a foggy nights, instead of saying as a day, I should mention it as a foggy nights, we can see the visibility of the automobile headlights. ಅಲ್ವಾ, ಒಂದು ತುಂಬಾನೇ ಮಂಜಿರ ಪ್ರದೇಶದಲ್ಲಿ ರಾತ್ರಿ ಹೋಗ್ತಿದ್ದೀರಾ ಅಂದಾಗ ಏನಾಗುತ್ತೆ, ನಮ್ಗೆ ಮುನ್ಗಡೆ ಬರ್ತಾ ಇರೋ ವೆಹಿಕಲ್ಸ್ ನ ಲೈಟ್ ಕಾಣುತ್ತೆ. ದಟ್ ಈಸ್ ಆಲ್ಸೋ ವಾಟ್ ಇನ್ ದಿ ಫಾರ್ಮ್ ಆಫ್ ಅ ಕೋನ್. ವೈ? Once again, it is by your Tyndall effect. Able to see. Every day we are seeing it, but none at the other time we were not knowing what it is. But now we have got to know it. So whenever you are coming up with that situation, it should strike to your mind, okay, this is a phenomenon of your Tyndall effect, which is an optical property of your colloidal solution. Of course, now the question arises that, what is the reason for this Tyndall effect? ಅಲ್ವಾ, ಓಕೆ ಸರ್, ನೀವು ಹೇಳಿದ್ರಿ ಲೈಟ್ ಬರುತ್ತೆ, ಕೊಲಾಯ್ಡಲ್ ಮೇಲೆ ಬೀಳುತ್ತೆ, ಸ್ಕ್ಯಾಟರ್ ಆಗುತ್ತೆ. ಯಾಕೆ ಆಗಬೇಕು ಅಲ್ವಾ? ಬಿಕಾಸ್ ಸೈನ್ಸ್ ಆಲ್ವೇಸ್ ಸ್ಟ್ಯಾಂಡ್ಸ್ ಫಾರ್ ವೈ. ದ ಬೆಸ್ಟ್ ಕ್ವಶನ್ ಇಸ್ ವೈ. ರಿಮೆಂಬರ್, ಇನ್ ಆರ್ಡರ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ದ ಕ್ವಶನ್ ಆಫ್ ವೈ, ವಿ ಹ್ಯಾವ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ದಿ ಕಂಡೀಷನ್ಸ್. What are the conditions which is facilitating your Tyndall effect? One important condition which I would like to mention, remember, whatever the diameter of your dispersed particles are present, the diameter of dispersed particles which is present should be, or we can say should not be, should not be should not be much smaller, should not be much smaller than the wavelength of the light used. What we are saying, whatever the dispersed phase particles are present, its overall diameter should not be smaller than the wavelength of the light used. Wavelength of the light used. Why is it so? Because it is only possible whenever the dispersed particles diameter is not so much smaller than that of the wavelength of the light, then only your dispersed phase particles will be having the capability to scatter the light. Is this the only criteria? No. The second most important criteria, you just remember, there should be the greater magnitude, there should be the greater magnitude of the refractive indices. Okay, there should be a greater magnitude difference. There should be a greater magnitude difference between the refractive indices. In the refractive indices, Andre, in your lower class we have seen it, alva. Refractive indices of your dispersed phase, and a dispersion medium. So these are the two criteria only when we can see the Tyndall effect. First, what enagirbeku, whatever the diameter of your dispersed particles are there should not be much smaller than the wavelength of the light used. And the second one, there should be a much difference in the magnitude of the refractive indices of your dispersed phase and the dispersion medium. Only when these two conditions are existing, what we can observe, your Tyndall effect. What is this Tyndall effect? So whenever a light is passed through that of your colloidal solution, what we are observing is, when we are observing it through the microscope at a right angle, we can observe a bright cone. And this bright cone is mainly because of what? Yeah, by the scattering of the colloidal particles in a colloidal solution. So this phenomenon is called as Tyndall effect. So whenever you have been asked what is Tyndall effect, you have to answer in this way. Not this much is not the answer. Scattering of light by the colloidal particle in a colloidal solution is not the answer. You should be much accurate. Whenever a light is passed through a colloidal solution and it is observed at a right angles, yes, and observe at a right angles using a microscope, the path of the light is visible in the colloidal solution as a bright cone. It is mainly because of the what? Scattering of the light by the colloidal particles in all the directions. So this effect is called as what? Tyndall effect. Is that okay? Okay. What are the two main conditions? Diameter of the dispersed particles not much smaller than that of the wavelength of the light used. And the second one, greater the magnitude difference between the refractive index of dispersed phase and the dispersion medium. So if these two conditions are facilitating, of course we can see the Tyndall effect. So this is one of your optical property. Next we'll be going with that of your kinetic property. So guys, now let us look after the important another property of your colloidal particles, which is called as kinetic property. Kinetic property. Or in simple words, it is with respect to that of your movement. Alva. So we are going to understand this kinetic property under the heading called as that of your Brownian movement. Brownian movement. Remember, whatever the optical property was called as a Tyndall effect, basically it is the name of the scientist who first discovered it, Tyndall. Similarly, this Brownian is also a scientist's name who was first and foremost was able to understand why the particles or why the colloidal particles are moving and from where the colloidal particles are gaining the energy. So in the name of his honor, as an honor, we are giving the name of the kinetic property of the colloidal particles as Brownian movement. So whatever we are going to see, it was an initial assumption of the Brownian. Of course, we came to know that whatever the colloidal particles are moving, of course, it is mainly because of the repulsive forces. Alva. ಪ್ರತಿಯೊಂದು colloid ಮೇಲೂ ಒಂದು particular charge ಇರುತ್ತೆ. ಎಲ್ಲಾ ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಮೇಲೂ ಒಂದೇ ತರ ಚಾರ್ಜ್ ಇರುತ್ತೆ. ರಿಪಲ್ ಆಗುತ್ತೆ, ಮೂವ್ ಆಗುತ್ತೆ. ಸೊ ದಿಸ್ ವಾಸ್ ಅಂಡರ್ಸ್ಟುಡ್ ವೆನ್ ಆಫ್ಟರ್ ಅ ವೆರಿ ಲಾಂಗ್ ಪೀರಿಯಡ್ ಆಫ್ ಟೈಮ್. But when it was observed for the first time, what did the Brownian movement, or what did the Brownian said why the colloidal particles move, will be able to understand over here. What was its state of assumption? Remember, basically, if somebody asks you what do you mean by Brownian movement, remember it is the continuous random alva, it is a continuous random zigzag. It is a continuous random zigzag motion of colloidal particles in a colloidal solution. In a colloidal solution is called as what? As a Brownian movement. ಏನು ಹೇಳುತ್ತೆ ಬ್ರೌನಿಯನ್? ಕಂಟಿನ್ಯೂಸ್ ಆಗಿ ರ್ಯಾಂಡಮಲಿ ಜಿಗ್ಜಾಗ್ ಮೂವ್ಮೆಂಟ್ ಏನುಂಟು ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಇನ್ ಅ ಕೊಲಾಯ್ಡಲ್ ಸೊಲ್ಯೂಷನ್, ಆ ಒಂದು ಮೂವ್ಮೆಂಟ್ ನೇ ನಾವೇನಂತ ಹೇಳ್ತೀವಿ? ಬ್ರೌನಿಯನ್ ಮೂವ್ಮೆಂಟ್. ಸೊ ಆಫ್ ಕೋರ್ಸ್ ವೆನ್ ಹಿ ಅಬ್ಸರ್ವ್ಡ್ ಇಟ್, ಬೀಯಿಂಗ್ ಅ ಸೈಂಟಿಸ್ಟ್, he has to give a reason. What is the main reason for such a movement of the colloidal particles? He was not having the much knowledge of the charge or that those days. But then what did he give is a very much important reason, because it is also a major fact. ಯಾಕಂದ್ರೆ ಪ್ರತಿ ಒಂದು ಪಾರ್ಟಿಕಲ್ ಮೂವ್ ಆಗ್ತುಂಟಂದ್ರೆ ಅದ್ರ ಮೇಲೆ ಒಂದು ಎನರ್ಜಿ ಇರುತ್ತೆ ಅಲ್ವಾ? as we all know, it's a kinetic energy. So with the Brownian movement, of course he tried to explain the motion of the colloidal particles, but we also extracted the energy of the colloidal particles through his reason. Let us understand what did he give the reason. Remember, in order to understand that one, first I would like to ask you a question. So whenever I am saying as a colloidal solution, of course what we can say, a colloidal solution means which will be having a colloidal particles alva, plus ಏನಾಗಿರುತ್ತೆ, ಒಂದು colloidal medium ಇರುತ್ತೆ ಅಥವಾ ಒಂದು solvent ಇರುತ್ತೆ ಅಲ್ವಾ? ಸೊ ಆ ಸಾಲ್ವೆಂಟ್ ಏನಾಗಿರುತ್ತೆ? ಕೊಲಾಯ್ಡಲ್ ಸೊಲ್ಯೂಷನ್ ಆಗಿರುತ್ತೆ. ವಾಟರ್ ಆಗಿರ್ಬೋದು, ಯಾವ್ದಾದ್ರು ಬೇರೆ ಒಂದು ಸಾಲ್ವೆಂಟ್ ಆಗಿರ್ಬೋದು, or any other types of the phase. But when I am considering as a liquid, so now my question is, colloidal particles in a size ಗೊತ್ತು ನಮ್ಗೆ, ಏನಾಗಿರುತ್ತೆ ಅಲ್ಲಿ 1 nanometer ಇಂದ 1000 nanometer ಒಳಗೆ ಇರುತ್ತೆ. ಸಾಲ್ವೆಂಟ್ ಇಂದ ಏನಾಗಿರುತ್ತೆ? ನಾವು ಪಾರ್ಟಿಕಲ್ಸ್ ನ ನೋಡಬಹುದಾ? ಅಫ್ ಕೋರ್ಸ್ ನಾಟ್. ಯಾಕೆ? ಬಿಕಾಸ್ ಇಟ್ ವಿಲ್ ಬಿ ಹ್ಯಾವಿಂಗ್ ದಿ ಪಾರ್ಟಿಕಲ್ ಸೈಜ್ ಆಫ್ ಲೆಸ್ ದನ್ 1 nanometer. ಹಾಗಾದ್ರೆ ಅರ್ಥ ಏನಾಗುತ್ತೆ ಇಲ್ಲಿ ಅಂದ್ರೆ, colloidal solution ಅಲ್ಲಿ colloidal particles in a diameter will be somewhat bigger when considered to that of a colloidal medium. In simple words ಅಲ್ಲಿ ಹೇಳಬೇಕು ಅಂದ್ರೆ, dispersed phase ಅಲ್ಲಿ ಇರೋ particles ಇನ ಸೈಜು ದೊಡ್ಡ ಆಗಿರುತ್ತೆ ಯಾವಾಗ ಯಾವ್ದ್ರ ಜೊತೆ ಕಂಪೇರ್ ಮಾಡಿದಾಗ? ನಿಮ್ಮ ಡಿಸ್ಪರ್ಷನ್ ಮೀಡಿಯಂ ನ ಕಂಪೇರ್ ಮಾಡಿದಾಗ. ಇಟ್ ಇಸ್ ನಾಟ್ ಮೆರಿಲಿ ಐ ಆಮ್ ಸೇಯಿಂಗ್, ಯು ಹ್ಯಾವ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಇಟ್ ಅಲ್ವಾ? ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ನ ನಾವು ಪಾರ್ಟಿಕಲ್ ಸೈಜ್ ನ ನೋಡಬಹುದು. ಆ ಪಾರ್ಟಿಕಲ್ ನ ನಾವು ಕ್ಯಾನ್ ಏಬಲ್ ಟು ಸಿ ಇಟ್ ಬೈ ಯೂಸಿಂಗ್ ಸರ್ಟನ್ ಮೈಕ್ರೋಸ್ಕೋಪ್. ಬಟ್ ಕ್ಯಾನ್ ವಿ ಸಿ ದಿ ಪಾರ್ಟಿಕಲ್ಸ್ ಆಫ್ ಎ ಡಿಸ್ಪರ್ಷನ್ ಮೀಡಿಯಂ? ಅಫ್ ಕೋರ್ಸ್ ವಿ ಕ್ಯಾನ್ ಸಿ. ಯಾವಾಗ? ಒಂದು ರೇಂಜ್ ನ ನಾವು ಫಿಕ್ಸ್ ಮಾಡ್ಕೋಬೇಕು, ವಿಚ್ ವಿಲ್ ಯು ವಾಟ್ ಮೋರ್ ದ್ಯಾನ್ ದಟ್ ಆಫ್ ಯೋರ್. ಆ ರೇಂಜ್ ಏನಾಗಿರುತ್ತೆ? ಮೋರ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಆಗಿರುತ್ತೆ. ಯಾಕೆ? ಸೈಜು ಅತಿ ಚಿಕ್ಕವಾಗಿರುತ್ತೆ. ಹಾಗಾದ್ರೆ ಅರ್ಥ ಏನಾಯ್ತು? ಇಫ್ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ದಿಸ್ ಇಸ್ ದಿ ಸೈಜ್ ಆಫ್ ಯೋರ್ ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ which is from 1 nanometer to that of your 1000 nanometer. Remember, it is which one of dispersed phase particles. ನಿಮ್ಮ dispersion medium ಇಂದ ಏನಾಗಿರುತ್ತೆ? Which will be very less, which will be nearly less than that 1 nanometer. Able to understand? ಯಾಕೆ ಇದನ್ನ ಹೇಳಿದೆ ಅಂದ್ರೆ ಈಗ ಗೊತ್ತಾಗುತ್ತೆ. Because whatever the reason he is giving, it mainly depends upon its size. So what does he says is basically, so whenever we are talking about a colloidal solution, of course we talk about its continuous random zigzag motion. So what does Brownian says is, particles of dispersed medium, ಏನು ಹೇಳ್ತಾನೆ? particles of the dispersed medium are moving very fast. ಯಾಕೆ ಫಾಸ್ಟ್ ಅಂತ ಕೇಳಿದಾಗ, ಬಿಕಾಸ್ ಕಂಪೇರಿಟಿವ್ಲಿ ಸೈಜ್ ಇಸ್ ಲೆಸ್, ಸೊ ಇಟ್ ವಿಲ್ ಬಿ ಮೂವಿಂಗ್ ವೆರಿ ಫಾಸ್ಟ್ ಅಲ್ವಾ? ಒಂದು ತುಂಬಾನೇ ದಪ್ಪವಾದ ವ್ಯಕ್ತಿ ಮತ್ತು ತುಂಬಾನೇ ತೆಳ್ಳಗಿರೋ ವ್ಯಕ್ತಿ ಒಂದು 100 ಮೀಟರ್ ರೇಸ್ ಓಡಿಸಿದ್ರೆ ಏನಾಗುತ್ತೆ? ಯಾರು ಗೆಲ್ತಾರೆ? ಏನಾದ್ರು ಅವನಿಗೆ ಕಾಲ್ ಪೆಟ್ಟು ಬಿದ್ದಿದ್ರೆ ಯಾರಿಗೆ ಸಣ್ಣ ನೀರವರಿಗೆ ಅವನು ಸೋಲ್ತಾನೆ. ಅದರ್ವೈಸ್ ಇನ್ ಜನರಲ್ ಕೇಸ್ ವಾಟ್ ಹ್ಯಾಪನ್ಸ್, ಅಫ್ ಕೋರ್ಸ್ ಯಾರಿಗೆಲ್ಲದು ಒನ್ ಹೂ ಇಸ್ ವೆರಿ ಥಿನ್. ಎಸ್, ದ ಸೇಮ್ ಕ್ರೈಟೀರಿಯಾ ಓವರ್ ಯು. ಯಾವ್ದು ಸೈಜ್ ತುಂಬಾನೇ ಕಮ್ಮಿ ಉಂಟು ಏನಾಗ್ತಾ ಇರುತ್ತೆ, ತುಂಬಾನೇ ಅತಿ ಫಾಸ್ಟ್ ಆಗಿ ಅದು ವೇಗ ಇರುತ್ತೆ. ಇಟ್ ಇಸ್ ಮೂವಿಂಗ್ ವೆರಿ ಫಾಸ್ಟ್. So what does it says is, whenever we are considering a colloidal solution, do remember particles of the dispersed medium are moving very fast. But what happens, of course, this dispersion medium also contains that of your colloidal particles, alva. So when they are moving very fast, they hit or they colloid. And they hit which one? They hit the colloidal particles. They hit the colloidal particles. ಏನಾಗ್ತಾ ಇತ್ತು, when the particles of the dispersion medium are continuous, very fast they are moving. ನಾವು ತಗೊಂಡಿರೋದು colloidal solution. Dispersed medium ಇದೆ, dispersed phase ಇರುತ್ತೆ. So when these particles of dispersed medium are moving very fast, what happens, at certain interval of time or certain criteria, they are going to hit the colloidal particles also, because they are also existing in that medium. So at that moment what happens is, remember, very much important, he says, whatever the kinetic energy, of your dispersed medium is there, whatever the kinetic energy of your dispersed medium is there, it is going to get transferred, to that of your dispersed phase particles, he says. Very much interesting, alva. ಏನು ಹೇಳುತ್ತೆ, particles of the dispersed medium are moving very fast. At that interval of time, they are all going to hit the colloidal particles. So ಆ ಒಂದು collision ಆದಾಗ ಏನಾಗುತ್ತೆ, whatever the kinetic energy of your dispersed medium particles were there, they are transferred to that of your dispersed phase particles. Yeah. So when the dispersed phase particles gain the kinetic energy, what happens? They also will move. They will also try to move. But what is the main thing we are going to observe is, whatever the movement of the dispersed phase is there will be less than that of the movement of your dispersion medium. Why? Because he says the main reason for the movement difference is about the particle size. Whatever the large size is there, large size of your dispersed phase particles will try to move those particles very slowly. But whereas that of the dispersed medium travels very fast. So this is the reason he gives why does your colloidal particles are moving very speed. Why they are traveling in a very high speed. ಯಾಕೆ ಅಂದ್ರೆ basically whenever particles of a dispersed medium are moving very fast, they are going to hit your colloidal particles. Yes. So when they hit, what happens? Of course, the dispersed phase particles are going to acquire a kinetic energy. ಎಲ್ಲಿಂದ ಬಂದ kinetic energy? They get transferred from that of your dispersed medium. So ಅವಾಗ ಏನಾಗುತ್ತೆ, ಈ dispersed phase particles ಕೂಡ ಮೂವ್ ಆಗುತ್ತೆ. ಬಟ್ ಅದರ ಸೈಜ್ ದೊಡ್ಡದಾಗಿರೋ ಕಾರಣದಿಂದ ಏನಾಗುತ್ತೆ, they will be moving very slowly, which is observed under your ultra microscope. So this is the reason he gives, that why does and how does your dispersed phase particles or your colloidal particles are in a continuous random zigzag motion. Okay, but if you make a keen observation of your Brownian movement, you can just observe the important things over there. What is that? So whatever the movement is there, that is a Brownian movement, it is independent. ಏನು ಹೇಳ್ತಾನೆ, it is independent of nature of colloid. ಅಲ್ವಾ, ಯಾವ ತರ ಕೊಲಾಯ್ಡ್ ಬೇಕಾದ್ರೆ ಇದ್ರೆ ಅವ್ನು ಯಾವ ತರದ್ದು ಅದ್ರ ಬಗ್ಗೆ ಸ್ಪೆಸಿಫಿಕೇಶನ್ ಕೊಡ್ತಾ ಇಲ್ಲ. ಸೊ ದಿಸ್ ಬ್ರೌನಿಯನ್ ಮೂವ್ಮೆಂಟ್ ಥಿಯರಿ, ವಾಟ್ ಎವರ್ ಇಟ್ ಇಸ್ ದೇರ್, it is what? Independent of your nature of the colloid. But the most important thing, he is depending upon what? The size of the particle. The size of the particle. Alva? Illadu colloidal particle size kammi idre, of course it will be moving very fast. And along with this one, he also states an assumption of your viscosity. Viscosity ಅಂದ್ರೆ ಅರ್ಥ ಏನು? ಒಂದು ಲಿಕ್ವಿಡ್ ಮೇಲೆ ಇನ್ನೊಂದು ಲಿಕ್ವಿಡ್ ಎಷ್ಟು ಬೇಗವಾಗಿ ಫ್ಲೋ ಆಗಬಹುದು ಅನ್ನೋದನ್ನ ವಿಸ್ಕಾಸಿಟಿ ಅಂತೀವಿ. ಯು ಜಸ್ಟ್ ರಿಮೆಂಬರ್, ಯು ಜಸ್ಟ್ ಟೇಕ್ two beakers, one is having a water and another is having an honey, and you just drop a small metal ball na on drop madana. ಯಾವ್ದಲ್ಲಿ ಬೇಗ ಹೋಗುತ್ತೆ? ಮಾರ್ಕ್ ಮೈ ವರ್ಡ್ಸ್, ಯಾವ್ದಲ್ಲಿ ಬೇಗ ಹೋಗುತ್ತೆ? ಅಫ್ ಕೋರ್ಸ್ ವಾಟರ್ ಅಲ್ಲಿ ಬೇಗ ಹೋಗುತ್ತೆ ಅಲ್ವಾ? ಸೊ ಹಾಗಾದ್ರೆ ವಾಟರಿನ ವಿಸ್ಕಾಸಿಟಿ ಏನು? ವಿಚ್ ಇಸ್ ಲೆಸ್ ವೆನ್ ಕಂಪೇರ್ಡ್ ಟು ದಿ ಹನಿ, ಇಟ್ ಇಸ್ ಮೋರ್. This was the case when you have taken your metal ball of the similar dimension. Now what I will do is, basically I will take the two beaker which is having the honey itself. ಎರಡಲ್ಲೂ ಹನಿನೇ ಉಂಟು, ಮೀಡಿಯಂ ನಾನು ಸೇಮ್ ಇಟ್ಟಿದ್ದೀನಿ. ಒಂದಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀನಿ, ಒಂದು ಮೆಟಲ್ ಬಾಲ್ ನ ಅತಿ ದೊಡ್ಡವಾದ ಮೆಟಲ್ ಬಾಲ್ ನ ತಗೊಂತೀನಿ, ಇನ್ನೊಂದು ಏನ್ ಮಾಡ್ತೀನಿ, ಸಣ್ಣವಾದ ಮೆಟಲ್ ಬಾಲ್ ನ ತಗೊಂತೀನಿ. ಈಗ ಯಾವ್ದು ಬೇಗ ಹೋಗುತ್ತೆ ಅನ್ನೋದು ಇಂಪಾರ್ಟೆಂಟ್ ಅಲ್ವಾ? ಅಫ್ ಕೋರ್ಸ್ this will move fast. Yes, because it will be having much restrictions to flow. It will be an easily seep through it, the honey, and it will go to the bottom and it will fall. So hagare artha enu, whatever this movement or whatever the energy which will be associated with that of your dispersed phase particles, it will be depending upon the size. Lesser the size, kinetic energy will be more. Alva? Ade reeti viscosity kammi untu, faster will be the motion. So that is the reason Brownian movement was considered, and it was also able to explain why does the particles are not able to settle. So ಏನಾಗುತ್ತೆ, ಕಂಟಿನ್ಯೂಸ್ ಹೊಡೆದಾಟ್ಕೊಂಡ ಒಂದು ಸಿನಾರಿಯೋ ಕ್ರಿಯೇಟ್ ಆಗ್ತಾ ಉಂಟು. ಡಿಸ್ಪರ್ಸ್ ಮೀಡಿಯಂ ಪಾರ್ಟಿಕಲ್ಸ್ ಮತ್ತೆ ಡಿಸ್ಪರ್ಸ್ ಫೇಸ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಏನಾಗ್ತಾ ಇರುತ್ತೆ, ಗುದ್ದಾಡ್ತಾ ಇರ್ತಾನೆ ಇರ್ತವೆ. ಆ ಗುದ್ದಾಡದಿಂದ ಏನಾಗುತ್ತೆ, ಎವ್ರಿ ಟೈಮ್ ಡಿಸ್ಪರ್ಸ್ ಫೇಸ್ ಪಾರ್ಟಿಕಲ್ಸ್ ವಿಲ್ ಬಿ ಮೂವಿಂಗ್, so they will not settle, which is the most important criteria for your colloids alva. It should not settle, it should be in a continuous random motion. And it's also by the Brownian movement which was able to explain the stability of this sound. ಈ continuous movement ಇಂದನೇ ನಾವೇನ್ ಹೇಳ್ತೀವಿ, your colloids are stable. ಸೊ ಆ ಒಂದು ಕಂಟಿನ್ಯೂಸ್ ಮೂವ್ಮೆಂಟ್ ನ ಬ್ರೌನಿಯನ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿರ್ತಾನೆ ಅವನ ಪೀರಿಯಡ್ ಅಲ್ಲಿ, and that was also in a proper way ಅಲ್ವಾ? ಸೊ ಏನ್ ಹೇಳ್ತಾನೆ ಅವನು, ಇಟ್ ಇಸ್ ಅ ಲಾಜಿಕಲ್. ಡಿಸ್ಪರ್ಷನ್ ಮೀಡಿಯಂ ಇರೋ ಪಾರ್ಟಿಕಲ್ಸ್ ತುಂಬಾನೇ ಸಣ್ಣ ಶೇಪ್ ಇರೋ ಕಾರಣದಿಂದ, ಸಣ್ಣ ಡೈಮೆನ್ಷನ್ ಇರೋ ಕಾರಣದಿಂದ ಏನಾಗುತ್ತೆ, ಅತಿ ಬೇಗವಾಗಿ ಓಡಾಡ್ತಾ ಇರ್ತವೆ. ಸೊ ಅವಾಗ ಅದು ಮಧ್ಯದಲ್ಲಿ ಎಲ್ಲಾದ್ರೂ ನಿಮ್ಮ ಡಿಸ್ಪರ್ಸ್ ಫೇಸ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಬಂತು ಅಂದ್ರೆ ಏನಾಗುತ್ತೆ, ಅದು ತನ್ನ ಎನರ್ಜಿನ ಡಿಸ್ಪರ್ಸ್ ಫೇಸ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಗೆ ಕೊಡುತ್ತೆ. ಆ ಡಿಸ್ಪರ್ಸ್ ಫೇಸ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಗೆ ಒಂದ್ಸರಿ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಹೋದಾಗ ಏನಾಗ್ಬಿಡುತ್ತೆ, ನಿಮ್ಮ ಡಿಸ್ಪರ್ಸ್ ಫೇಸ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಕೂಡ ಮೂವ್ ಆಗಕ್ ಸ್ಟಾರ್ಟ್ ಆಗುತ್ತೆ. ಸೊ ಆ ಒಂದು ಮೂವ್ಮೆಂಟ್ ನೇ ನಾವೇನಂತ ಹೇಳೋದು, ನಿಮ್ಮ ಬ್ರೌನಿಯನ್ ಮೂವ್ಮೆಂಟ್. ಸೊ ಆ ಒಂದು ಮೂವ್ಮೆಂಟ್ ಯಾವ್ದ್ರ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿರುತ್ತೆ, ಒಂದು ಸೈಜ್ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿರುತ್ತೆ, ಇನ್ನೊಂದು ವಿಸ್ಕಾಸಿಟಿ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿರುತ್ತೆ. ಸೊ ಓವರ್ ಆಲ್ ಈಗ ಬ್ರೌನಿಯನ್ ಮೂವ್ಮೆಂಟ್ ನಮ್ಗೆ ಏನ್ ಹೇಳುತ್ತೆ, ಇಟ್ ಕ್ಯಾನ್ ಈಸಿಲಿ ಎಕ್ಸ್ಪ್ಲೈನ್ ದಿ ಸ್ಟೆಬಿಲಿಟಿ ಆಫ್ ಯೋರ್ colloids, and it also answers the question that why does your colloidal particles are in a continuous random motion. Two most important properties we have looked today. One was an optical property called as that of your Tyndall effect, which was the scattering of the light by your colloidal particles. And the second most important thing was your kinetic property, which was called as a Brownian movement, which is a continuous zigzag random motion of your colloidal particles in a colloidal solution. Each of the properties has their own criteria. We have look after it. Yeah. In the next video, we are going to see one of the most interesting thing. What is that is, how does your colloidal particles absorb the charges? Alva? ಅವತ್ತಿಂದನೂ ಹೇಳ್ತಾನೆ ಇದ್ದೆ, ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಮೇಲೆ ಯಾವುದೋ ಒಂದು ಚಾರ್ಜ್ ಇದ್ರೆ ಅದೇ ಚಾರ್ಜ್ ಎಲ್ಲಾ ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಮೇಲೆ ಇದ್ದೇ ಇರುತ್ತೆ. ರೀಸನ್ ಬೇಕಲ್ಲ, ಯಾಕೆ ಸರ್ ಹಾಗೆ, ಯಾಕೆ ಒಂದೇ ತರ ಕೊಲಾಯ್ಡಲ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಮೇಲೆ ಚಾರ್ಜ್ ಫಸ್ಟ್ ಆಫ್ ಆಲ್ ಎಲ್ಲಿಂದ ಬರುತ್ತೆ ಅನ್ನೋದು ಇಂಪಾರ್ಟೆಂಟ್ ಅಲ್ವಾ? ಸೊ ದಟ್ ವುಡ್ ಬಿ ಸೀನ್ ಇನ್ ಅವರ್ ನೆಕ್ಸ್ಟ್ ವಿಡಿಯೋ.